Hello everyone, welcome to my channel. So today we'll try to learn a very useful technique that is used to solve diophantine equations. So that is called Fermat's method of infinite descent. So in short we can also write it as FMID. So let me just highlight the name. Okay, so it was from the name itself you can guess it was derived or discovered by Fermat, and around he actually around maybe around 1631 or around that time. So let us see what is this method of infinite descent. So let P be a property concerning non-negative integers and let Pn, so this is a sequence where n is greater than or equals to 1 because we are taking non-negative integers, be in the sequence of propositions so what is that? That is Pn is some property that n satisfies. So n satisfies the property P. So that property we have already defined. So this is a proposition. So now this method is useful in proving that the proposition Pn is false for large enough n. So the following method is useful in proving that proposition Pn is false for all large enough n. So let us see what is the method. So we take, so let k be a non-negative integer, and we suppose that we take two conditions. So the first condition is pk is not true, that is this k does not satisfy the property P. And the second one is, so whenever Pm is true for any integer that is larger than k, true for m greater than k. So here m also belongs to the positive integer z plus. Then there must be some smaller value of j. So then there exists j that is also integer such that j lies between k and m. So for which the proposition is true, that is pj is true. So if these two things holds, then we can conclude that then Pn is false for all n that is bigger than equals to k. So more or less this is the method. So yes, so seeing these statements, you can feel a relation between induction, right? So this is just nothing but the contrapositive statement of the strong induction. So that is a observation. So note that. So this is just the contrapositive of strong induction. Which is applied to the negation of the proposition Pn. Pn. So this method we usually call that is described. This is called the method of finite descent method. So the method described the finite descent. So next we'll see what is that Fermat's method of infinite descent. So that is the next thing. So I think up to this is clear. So maybe we'll quickly recall maybe at the end. So the FMID or the Fermat's method of infinite descent. So that can be formulated as follows. So let k be a non-negative integer. And suppose whenever Pm is true for an integer m greater than k, so then there must be some smaller integer j, where this j lies between m and k. So here note that j is strictly greater than k, because the previous one was j is greater than equals to k, for which pj is true. Then we can say that Pn is false for all n greater than k. So so more or less let us see what is happening. So that is, if there were an n for which Pn was true, we can construct a sequence n then which is greater than n1, decreasing sequence like that, all for which would be greater than k. But the thing is, non-negative integers, there cannot be such infinite decreasing sequence that can exist, right? So that will be the contradiction. So let me write. So if there was an n for which Pn is true, the proposition or the property is true, so one can construct a decreasing sequence. So n1 is smaller than n and so on, all of which will be greater than k, right? But the thing is, since we are taking only non-negative integers, so such decreasing sequence, infinite decreasing sequence, does not exist, since we are only non-negative integers. No such infinite decreasing sequence exists. So this FMID has two variants. I think this is more or less is clear. So this FMID has two variants. We'll see both of them. So sometimes the first variant is useful, sometimes the second variable is so the second variant is useful. So let us check the first variable. So what it is saying? So there is no sequence of non-negative integers n1 greater than n2 and so on. This decreasing one, and in some situation it is convenient to replace this FMID variant 1 by the following equivalent form. So if n0 is the smallest positive integer n for which Pn is true, then Pn is false for every integer n that is less than n0. So let me write down. So there is an equivalent form of this one. So if n0 is the smallest positive integer, n for which Pn is true, then this Pn is false for all n that is smaller than n0. And the second variant is it says that so if a sequence of non-negative integers n i's where this I is greater than equals to 1 satisfies the inequality. That is it decreasing. So n1 is greater than n, or you can say non-increasing. Then there exists an I naught such that after a certain state it becomes all the terms are equal. So n I naught is equals to n I naught plus 1, n I naught plus 2, and so on. So this is the second variant. So let us quickly recall or recap what we learned. So P is a property that only involves non-negative integers. Then we are considering a sequence where Pn denotes n if n satisfies the property P. Then suppose this is the finite descent method. So k is a non-negative integer, and suppose that pk is not true, and whenever pm is true, I can find an integer j which is between k and m such that bj is true. Then these two things implies that pn is false for all n greater than equals to k. And FMID is finite, that infinite descent. That is, k is a non-negative integers, and suppose that pm is true for all m greater than k, then there must exist some integer j between k and m for which pj is true. Then pn is false for all n greater than k. So these are, next we had two variants of FMID. So there is no sequence of non-negative integers such that n1 greater than n2 and so on. And if n0 is the smallest positive integer n for which pn is true, then pn is false for all n greater than n0. So that is the equivalent condition. And the second variant is if a sequence of non-negative integers ni has satisfied the inequalities thing, then after a certain stage, or I will find an I naught such that from I naught plus 1 onwards, all of the terms will be equal. So we'll see application or through examples in the next video. So thank you for watching, and subscribe the channel for more such videos.